Alright, so we're going to talk about how to determine if a number is prime. I wrote down three numbers here: 17, 199, 4,223. So maybe pause the video and see if you can determine a way of checking whether these numbers are prime. Don't worry about actually doing it, just think about how you do it. So pause the video now and think about that. Okay, well, one way you might have come up with is, well, prime numbers definitely have no other factors than one in itself, so let's just check if these guys have some other factor. So you could say, well, I guess I'll just try every number from 2 to 16 to see if it's a factor of 17 via long division or our divisibility rules or whatever. And you could say, well, that's not too bad. It would take a little bit of time, but not too long to do this. 199, you could do the same idea, but it would take far longer to check every number from 2 to 198. And if there was some number like 4,223, it would take even longer to determine that. And you probably couldn't even do that in a day. To do all of those thousands of long divisions would be a crazy thing to do. So, is there a more efficient and better way? So we can start thinking about this. So, the first idea, let's talk about composite numbers. So, if you remember with composite numbers, they have factors that aren't one in itself. Of course, that's the definition. But remember the factors come in pairs. And that's kind of the key idea here. For example, if we had a number like 18, 18 you can write as 2 times 9, or maybe, I don't know, what else can we do? 3 times 6, right? Or something like 144, you could write as 12 times 12 if you like, or you could write it as 16 times 9 if you like, whatever. But let's think a little more deeply about this. Well, if we think about it, if we look at these factors, 12 times 12 is going to be a little bit special case in some sense. So let's leave that for a second. But for the others, there's always going to be one factor that's less than the square root of the number and one factor that's greater. So you can check the square root of 18 via your calculator if you like, but you can also just kind of estimate it. I know the square root of 16 is 4. I know the square root of 25 is 5. So the square root of 18 is going to be somewhere between 4 and 5. So I know that one of the factors is going to be less than the square root, and the other factor is going to be bigger than the square root. That's always going to be the case. They can't both be bigger than the square root or less than the square root, because then if they were both bigger than the square root, then you would have a number bigger than 18. If they were both less than the square root of 18, then you'd have a number smaller than 18. One has to be bigger, one has to be smaller. Same thing with 3 and 6. 3 is smaller than square root 18, 6 is bigger than square root 18. 144, well, we know the square root of 144 is 12. One factor is going to be bigger, one factor is going to be smaller. The only case is, well, maybe if it is a square number, like 144, because that's 12 squared, well, you can write it as 12 times 12, so in this case, the factors are both exactly equal to the square root. So that's the first idea I want to stress to you guys. So this is great. In fact, if we think about what we've learned from this analysis, we can say, well, if there's always going to be a factor less than the square root, or maybe equal to the square root, there's always going to be one in any factorization, well, we don't need to check all numbers now. So our first realization is we only need to check numbers that are less than or equal to the square root of n. If we wanted to see if n was prime, well, we'd only need to check numbers less than or equal to the square root. Because if we get one factor, we know we have the other factor bigger than the square root that pairs with it. So we only need to check numbers less than or equal to the square root of n. The other realization is as follows, and this is important. Remember, every number can be built up as a product of primes. Something like 9 here, for example. 9 I can write as 3 times 3. And if 9's a factor, well, remember that result, I think it was theorem 4 it was labeled. 3's a factor of 9, 9's a factor of 144, so 3's a factor of 144. So what that means, since there's always going to be prime factors in every factor, well, I don't need to just check all numbers less than the square root. I need to check only prime numbers less than or equal to the square root of your number. So that's a really cool idea. So that really simplifies our calculation. So let's prove this. Let's prove this using a mathematical proof, a nice if-then statement, to make sure that this definitely holds. But it is basically this idea. So here's our result that we're going to prove. I'm just expressing it in the language of mathematics a little more exactly than what we talked about it. Let's read it. All right. Let n be a natural number or a counting number, and let n not be 1. So it's going to be 2 or greater. All right? So we have a nice if-then statement. If for all primes p that's less than or equal to the square root of n, it's the fact that p isn't a factor of n. So for every prime less than the square root of n, if p isn't a factor, then n is prime. That's what we want. Now, to prove this, it's a little bit easier if we prove the contrapositive instead of the original statement. Remember, the contrapositive is where you flip and reverse the if and then parts of your conditional statement here. And remember, these guys are logically equivalent. They mean the same thing. So it's just written in a different form. So let's do it. So here it is. It's saying that we're going to flip and reverse each part. So the negation of q, so q is n is prime, so the negation is n is not prime. So, oh, sorry, I wrote down a p here. It should be an n. Let me erase this and write n. If n is not prime, so remember, n's not 1. I stated initially that we're not counting n to be 1. So if n isn't prime, and we said it's not 1 anyway up here, then n must be composite. If n is a composite number, then the negation of p. So what's the negation of p? Well, we needed to negate for all primes less than the square root of n, p isn't a factor. So remember, we're negating a universal quantifier, a for all. So remember, to negate that, the for all changes to an existential quantifier, a there exists or a there is. So rather than for all primes less than the square root of n, It's there is a prime less than the square root of n, and then we just negate this part here. So rather than p isn't a factor of n, it's going to be p isn't a factor of n, which means p is a factor of n. So this is what we're going to prove. If n is composite, then there is a prime less than the square root of n where p is indeed a factor. All right, so we're going to prove this in a little bit different of a way. I talked about it a little bit when we talked about logic, but let me remind you what it is. It's going to be a proof by contradiction. And what we're going to do is we're going to pretend that there is a counterexample and show that if there is, mathematics breaks. So if you remember, we had this truth table for an if-then statement. And remember that this conditional statement is only false when the if part is true and the then part is false. That's the only time a conditional statement is false. So we want to show that this row never happens. So if you remember, one way we did it is we assume the if part is true, and then we show that the then part must be true. Another way is to assume the then part is false and show that the if part must be false, so that we're avoiding this row. But the other way, a proof by contradiction, is we pretend that the if part is true and the then part is false, and we show that mathematics breaks. So we show there is a counter, or we pretend there is a counterexample where the if part is true and the then part is false, and we show something about mathematics breaks. So that is what we're going to do. We're going to assume that the if part is true and then part false, and show math breaks. There's some contradiction that will come up. And the contradiction that we're going to get is we're going to get that n is going to be less than itself. Not less than or equal to, just less than. That's going to be our contradiction. That's going to be how math will break. So let's go ahead and talk about how we're going to prove it on the next slide. So the idea here is we're going to use the fact that all composite numbers definitely have two prime factors. They could be the same prime factor, but they definitely have two of them. So we can pull out the two smallest prime factors that a composite number has. We know composite numbers have two or more factors, and each factor can be factored into its prime factor, so we know that every composite number is going to have at least two prime factors. Again, they could be the same. So the idea is we're going to take the two smallest ones. We're going to take, in the case of 12 I can write as 2 times 2 times 3. I am going to think of 12 as these two times the rest, and the rest here is just the 3. 9, well, 9 is just made up of two prime factors, and that's it, 3 times 3. So I'm going to take those, and I'm thinking of the rest, so there's a number there, I'm going to say it's like multiplying by 1. So 3 times 3 times 1, putting that there, and you'll see why in a second, just for notation. 110 is 2 times 5 times 11, so I'm going to pull out the 2 and the 5. 77 is 7 times 11, and maybe something like 36 is 2 times 2 times 3 times 3. Again, I'm going to take the two smallest, there they are there, and I am going to just think of the 3 and the 3 as the rest. So just to understand the notation I'm about to use, I'm going to call one of the small primes P, the other small prime Q. And the rest I'm going to call C. So in the case of 12, P and Q are 2 and 2, and C is 3. 9, well, P and Q are 3 and 3, and this 1 is going to be C. 110, 2 is P, 5 is Q, 11 is the rest, C. 77, P, Q, and C is, of course, just 1. And 36, we have P is 2, Q is 2, and C is going to be the rest. C is going to be 9 in this case, 3 times 3, just whatever's left over. We don't really care about it. We're just picking out the stuff we care about. Okay, now that we have this idea, let's go ahead and do our proof. Remember, we need to assume there's a counterexample so that the if part is true and the then part is false. So assume there is a composite number. So that's the if part being true. Let's call it n. Where, well, if you remember the then part said there is a p less than the square root of n where p is a factor of n. So if we want to say that the then part is false, well, that means that for all primes p, they don't divide. So in that case, it must mean that where every prime factor let's write it like this, every prime factor of n is greater than the square root of n. If we're saying that the then part is false, the then part here is there is a prime factor less than the square root of n, well, if that's false, it must mean all prime factors are greater than the square root of n. So that's what we're going to assume. Okay, so we've set up our situation. The if part was true, the then part is false. So, what does that mean? Well, we called it n. All right. Since n is composite, we can pull out its two smallest prime factors, just like we did in the examples above. So we're going to write n as p times q times c. Let's actually name these prime factors. So prime factors, let me erase this colon here, p and q. So they're its two smallest prime factors. And c is the rest. So let's tell people what c is, where c is just some number. That could be 1, but it's definitely a whole counting number. Okay, so remember, since all prime factors are greater than square root n, this tells me that p is greater than square root n, and q is greater than square root n. Okay. Well, let's consider n again. So consider n, which is p times q times c. Okay, so what I'm going to do, if I replace p with square root n, well, since p is definitely bigger than square root n, or at least that's what we're assuming, p is bigger than square root n. If I replace p by square root n, I get an expression that's smaller. So I'm going to replace p with square root n. And if I do so, I get something that's smaller. So if you don't see that, pause the video and think about that a little bit. I'm replacing a bigger number with a smaller number. So the side with the smaller number is smaller. But I can do this again. I can replace q with square root n, and the expression gets even smaller. So in the first step, I'm replacing p with square root n and getting something smaller. In the second step, I'm replacing q with square root n and getting something smaller. In fact, maybe it's better to say this q. I'm replacing this q with square root n and getting something even smaller. And then, well, I also know, maybe I'll write it here, since c is definitely bigger or equal to 1, well, if I replace c with 1, then I get something definitely not bigger. It could be equal if c was already 1. But I'm going to get square root n times square root n, and then times 1. But I'm not even going to write it in, because multiplying by 1 doesn't do anything. Or if you think about it, if I don't multiply by a counting number, I'm going to get something even smaller, or at least no bigger. So, what is this? Well, square root n times square root n, well, by definition, that's just n. So, let's see what we did here. We have n is smaller than, and after a bunch of other steps where the inequalities keep getting smaller and smaller, so n is greater than n here. So we can say thus n is greater than n. But we know that's not true. But this is never true. So what we started with must be incorrect. So if we do assume there was this counterexample, a composite number where all the prime factors are greater than its square root, then we get that n is greater than itself. And since that, of course, never holds, that what we assumed must be wrong. There must be no counterexamples, so the original statement must be true. So again, we showed that if we assume there's a counterexample, mathematics breaks. We get that n is greater than itself, which makes no sense. Since mathematics breaks, there must be no counterexamples, so the original statement must be true. We're never in that dreaded row of the truth table. So let's do an example of how to use this, which is really cool. So let's say we wanted to determine if 199 was prime. Well, using the test for primality, remember we only have to check if the prime numbers less than the square root are factors. Now, if you have access to a calculator, you can type in square root of 199 and get what it is. But if you don't, say on a test or an exam where calculators aren't allowed, you can just estimate where the square root lives. So you can just calculate some square roots. I know you could even do it kind of even more coarsely. I know that the square root of 100 is 10, the square root of 400 is 20, so the square root of 199 is going to be somewhere between there. So then you could just calculate squares of some numbers to get kind of one smaller than it and then the next one bigger. So you can check 14 squared is 196, which is just smaller than square root 199, and 15 squared is 225, which is just bigger than square root 199. So the square root of 199 lives between these guys. So it's 14 and a bit. Once we have that, well, we know what primes we need to check. We need to check the primes less than square root 199. So what are these primes? Well, they are 2, 3, 5, 7, 11, and 13. So they're the primes that we'll have to check. Okay, let's go ahead and do it. So let's check 2 first. Is 2 a factor of 199? Well, no. And let's say why. Since 2 isn't a factor of the last digit of 9. Remember, to determine if a number is divisible by 2, the last digit has to be divisible by 2. So we can erase this question mark, and we can replace it by a cross there to say it's not equal to. Well, with 3, rather than kind of writing all of these out, it's a good idea to, on a test or exam or assignment, just to show how you know that. But we can do 3 here. Is 3 a factor of 199? Well, let's check. 9 plus 9 is 18, plus 1 is 19. 3 isn't a factor of 19, so 3 isn't a factor of 199. You can see where these divisibility tests come in. Now we don't need to check 4, because 4 isn't a prime number. We need to check 5. Is 5 a factor of 199? Of course it isn't. 5 isn't a factor of the last digit. It's not a 0 or 5. Is 7 a factor? Well, I'm going to leave that for a second. Is 7 a factor of 199? The reason is we don't have a nice test, so we're going to have to do some long division. But we have another test for 11, so we might as well do the test one first. Is 11 a factor of 199? You can check, and in fact it's kind of easy to see, that 1 minus 9 plus 9, the alternating sum. So this is 1 minus 9 plus 9 is 1. And is 11 factor of 1? It is not. Nothing is a factor of 1 besides itself. So 11 isn't a factor. And we have to check 13 as well. Is 13 a factor of 199? So there were some nice, easy divisibility rules we could use for 2, 3, 5, and 11. And anything else, we're just going to have to do some long division. Okay, it's not too bad. 7 into 199. 7 goes twice into 19 with 5 left over. 7 goes into 59 8 times with a remainder of 3. We have a remainder, so it's not a factor. So 7 isn't a factor. I can get rid of that question mark now. Okay, 7 isn't a factor. What about 13? You can check. 13 goes into 199 once. Subtract 13. We get 6. Bring down your 9. 13 goes into 69 4 times, maybe. Actually, not 4 times. That's going to give us 42. And that is it going to give us 42? Well, let's see. Anyway, I think 5 times will do it. 3 times 5 is 15. Carry your 1. 5 times 1 is 5. Plus 1 is 6. Get a remainder of 4. So 13 isn't a factor of 199 either. There we go. So none of these primes less than the square root of 199 are a factor of 199. So by the test for primality, we know 199 is prime. So try this example now. Check if 391 is prime. Follow the steps above. Figure out the prime numbers you need to check, and then check them. So pause the video now and see if you can do the test for primality at 391. Okay, now that you're back, you will find that the square root of 391 lives somewhere between 19 and 20. So you need to check all of the primes less than that. So that's going to be 2, 3, 5, 7, 11, 13, 17, and 19. So I'm not going to do out the work above here. It's the same idea, but I will tell you that once you check 17, let's see what happens. So 17 is 17 a factor of 391. In fact, you'll find that the others aren't. So if you do this correctly, you'll find that 2 isn't a factor, 3 isn't a factor, 5 isn't, 7 isn't, 11 isn't, 13 isn't, and 19 isn't as well. But 17, if we do the long division, 17 into 391, 17 goes into 39 twice, subtract, we get 34, remainder 5, 17 goes into 51, 3 times exactly. Hey, look, 17 times 23 is 391. So we can get rid of this question mark. We know it does indeed go into 391. So we can say, so 17 times 23 is 391. So 391 we can write as a product of two numbers that aren't one in itself. And we can say 391 is composite. It's not prime. And that's how the test for primality works.